Alright, so continuing on from section 8.1, we still have to cover section 8.2. So it's going to be very similar in a lot of ways. 8.2 is compared to 8.1. 8.2 covers the distribution of a sample proportion. And just a little review over section 8.1. Section 8.1, we were dealing with normal distributions. The original distribution, we either dealt with a normal distribution or a non-normal distribution, and then we remember that the sampling distribution I'll just say of x bar means the same thing as what we were talking about in the last section. The normal distribution will also be normal always, regardless of the size of n, our sample size. For a non-normal distribution, if the original distribution is non-normal, then we have to have n greater than or equal to 30 to be normal. Okay, so this n greater than or equal to 30, we'll actually see in section 8.2 that this n greater than or equal to 30 in section 8.1, it's kind of arbitrary, and we just give you, okay, if it's at least n, if n is greater than or equal to 30, it's going to be normal, the sampling distribution. Now, we'll actually find out that, I mean, for the, section 8.1 and for this class, that's fine. N greater than or equal to 30 will be normal. But we'll find out that it doesn't always work, and section 8.2 is an example. And so, again, this is because of the law of, not law of large numbers, the central limit theorem that this works. This is the central limit theorem, where we have a non-normal distribution. But the sampling distribution of x bar, if we have a large enough n, will have a normal distribution. That is the central limit theorem. And that's very strong because if we have a non-normal distribution, then we can't really do much with it. But if we take a sampling from it, and we know that we have a normal distribution from that, then we can calculate a lot of probabilities because we can do a lot of things with normal distributions, in which we couldn't not have done with the non-normal distribution. So let's go ahead and go into section 8.2. That was just a review of section 8.1. So section 8.2 is the sample or the distribution of a sample proportion. Now, you may not have, I'm going to teach this slightly different than what you probably have seen in your Math 243 class. You have seen distributions of a sample proportion, and I'm going to go over a lot of the same information, but I'm going to explain it a little bit differently, so maybe it'll give you a fresh perspective, and maybe it'll clarify a few things. Because you may have noticed that a lot of things may have been given to you, and they didn't really explain where it came from. So I'm going to make a lot of comparisons to section 8.1. So try to make that kind of parallel comparison and kind of see how they're similar. And you're going to actually have to do some of the work that I'm going to kind of just give you in this lecture. You're going to be doing some of this work in Lab 1. So I'll let you know when we get there. So I'm going to introduce a distribution that you've never heard of, but it actually explains our original distribution for a proportion. So, for example, let's just say that we're going to be asking someone a question. I don't know. something simple. Do you like ice cream or do you not like ice cream? That's a proportion, either yes or no. That's how proportions work. The proportion of people that like ice cream. So I'm going to give this distribution a name, and this is actually the name. You can look it up online. It's called a Bernoulli distribution. Named after, actually, I think it's named after Jacob Bernoulli. There's a bunch of brothers, famous mathematicians from the past. I think the guy that came up with this one was Jacob Bernoulli, one of the more famous brothers. There's several of them, whole family of Bernoullis actually. Anyways, the Bernoulli distribution. And so the idea is the probability. Remember, our random variable is usually called x. So the probability that x equals 1, representing, we got a yes, someone likes ice cream. The probability that x equals 1 is equal to p. Okay, and then the probability that x equals 0 would be the complement of p, because it has to be either yes or no, you like ice cream. So this represents a no, and that would be 1 minus p. So either you like ice cream or you do not like ice cream. Okay, and we'll actually find out that the mean mu. So we're defining our original distribution. The original distribution is known as the Bernoulli distribution. And we were all, like in section 8.1, the original distribution, we're given a mu and a standard deviation. So we're given mu and of the original distribution, in this case the Bernoulli distribution for sample proportions. The mu is equal to p. And then we also are given a standard deviation. The standard deviation of a Bernoulli distribution is the square root of p times 1 minus p. Okay? So this is actually really interesting, and hopefully you can kind of picture at least this line right here. This is exactly what we're dealing with in in section 8.2. Every time we do a trial, we ask one person, do you like ice cream? They're either going to say yes or no. And there's a designated proportion of people in the population that like ice cream. We don't know what it is necessarily, but let's just say it's P. Okay, that could be 75% of people like ice cream. And then the probability that do not like ice cream, which represents x equals 0, is 1 minus p. Okay, so that's how proportions work. You only have two possibilities, a yes or a no, or true or false, or whatever. Hopefully you realize that from Math 243. And we defined the Bernoulli distribution to be defined as mean equals to p, and sigma equals the square root of p times 1 minus p. And this is actually what you are going to be proving. This is lab 1. Okay, so you're going to be proving this, and then this is problem 1 of the of lab 1, and this is problem 2 of lab 1. And then there's a question 3, which you explain how this works into the central limit theorem. And remember, as n approaches, as n gets large enough, then we know that as we increase the sample size n, then we know that the distribution approaches a normal distribution. And so what we remember from section 8.2, if you remember, is that, well, Actually, let's just draw this really quick, just so that you can see the shape of the Bernoulli distribution. Let's just say that P in this case is 0.75, like we mentioned. So there's x equals 0 and x equals 1 in this case. And we mentioned that that the probability of 0 is 0.25 for the made up 1 minus p, and then the probability of 1 is 0.75. So as we can see, this original distribution, the original distribution has this shape right here. This is obviously not normal. So a Bernoulli distribution is non-normal. Okay? So comparing this to section 8.1, we're dealing with a non-normal distribution. So in order for a non-normal distribution, for the sampling distribution from the original distribution to be normal, we have to have a large enough sample size. Now in section 8.2, we'll notice that it's not quite n greater than or equal to 30. It's going to be, if you remember, n p 1 minus p is greater than or equal to 10. Okay? If np times 1 minus p is greater than or equal to 10, then we know that we have a normal distribution for the sampling distribution of p hat. So it's a little bit of review from section 8.2. This is kind of a new way of thinking of 8.2, and it kind of makes a connection with using original distribution, sampling distributions to explain kind of the similarity between 8.1 and 8.2, because 8.2 actually, the only reason we're able to do this is because of the central limit theorem. So let's go ahead and move on. And as you can see, this is non-normal. A normal distribution would look like that, something like that. So this is obviously non-normal. Okay, so now, like before, we're going to be taking a sampling from the original distribution. So, for example, from the example from before, we said the probability that x is equal to 1 is equal to 0.75, and the probability that x equals 0 is equal to 0.25. The probability that someone likes ice cream is 75%, and the probability that someone does not like ice cream is 25%, a proportion. It's either yes or no, with the given probabilities. And so similarly to section 8.1, we're given the original distribution, the exact known values, the parameters of the original distribution. In this case, p. We know what p is. So just like we knew what mu and sigma was in section 8.1. Now what we need to know is how large of a sample size do we need in order to obtain a normal distribution. We'll get to that in a little bit. We've kind of mentioned that with the np 1 minus p is greater than or equal to 10. But so imagine that we take our first sampling from this to get our, the shape of our sampling distribution. And let's imagine that we took a sample size of 100. N equals 100. So we're going to ask 100 people if they like ice cream or not. And so they'll say yes or no. Yes, meaning we got an x equals 1, and no, we got an x equals 0. So we essentially have, so just to let you know, yes equals, or I'll just say like ice cream, represents x equals 1, and do not like ice cream represents x equals 0. So let's just imagine that we have the first sampling of n equals 100, and I'm not going to, you can kind of imagine this, I'm not going to write all 100 out, but we have and remember that we have a proportion of 75% liking and not 25% not liking. So we're going to have a 1, 1, 0, 1, 1, 1, 0, 0, 1. Looks like binary, but anyways, which it kind of is because we only have options 1 and 0. But as you can see, we're going to continue this until we have 100 different values from the original distribution. And then we're going to take the average of this sampling, and how we define average in this case is not x bar. As you remember, it is p hat. P hat represents the average of ones and zeros, of the ones and zeros. So let's just imagine that we had 0.73. And then let's imagine that so that's the first sampling. And then imagine we took another sampling, another 100 values, and we got 0.68, and then imagine we do this again, and we got 0.71, and then we do this 1,000 times, and the last one is 0.7. Man, let's give it 0.75. So what we're going to do is we're going to do this 1,000 times to kind of imagine what the shape, if we have a sample, we can imagine what our sampling distribution is based off of gathering 1,000 different p hats, and it'll give us the general shape. And we'll notice actually that it is a somewhat normal distribution, centered at p. Well, we actually call this mu of p hat, the mean of our normal distribution, sampling distribution. Since our sampling distribution in this case contains all p hats, then we do mu sub p hat, like we did mu sub x bar before. And that will be equivalent to the average of all of these, and we expect the average to balance out to this 0.75. In general, it's p. In this case, it's 0.75. So in general, and it says this in the book, mu sub p hat is equal to p, our population proportion, okay, which is the proportion of our original distribution. And then we'll notice that the standard deviation is actually, so I'll just say sigma sub p hat. That's the distance from here to here. That sigma sub p hat is equal to, in general, it is equivalent to the square root of p times 1 minus p over n. If you remember that, and you can look in the book and you'll find this equation. So you may want to be taking this into consideration when you answer part 3 of the lab 1. So think about this. Think about this and this when you do lab 1 part 3 of your main post. And then you'll kind of want to expand on that and describe what this all means, and I mean, read the problem and kind of explain as much as you can. And one thing you really need to take into consideration, I probably mentioned this already, not taking into consideration, but instructions for lab 1 and all the labs is that you cannot post into lab 1. I mean, your first post into lab 1 is supposed to be your main post. Don't ask a question like, I don't understand lab 1, and into the lab 1 post, because or discussion, because then you'll be able to see what other people wrote. I want your first post to be your main post, answering the 3 questions. Okay, so anyways, please, yeah, go ahead and make sure it's your main post for the first post. And then you just follow the instructions. Anyways, so what we have here is we have the mean of our sampling distribution, p hat, is the population proportion of our original distribution. Similarly, sigma of p hat is equal to the square root of p times 1 minus p over n. You'll want to think about how this is similar to section 8.1 equation. And I'll go ahead and just give you a clue. Explain how this is equivalent to or similar to sigma over the square root of n. You want to think about that for part 3 in your comparison. And so anyways, yeah, this is the equation from section 8.1 and this is the equation from section 8.2. And you'll want to kind of compare this and you'll do some calculations and you'll figure out that there's a similarity. And you'll answer the central limit theorem part of the question. So anyways, and for this distribution with 0.75 and 0.25, then our sigma of p hat would be the square root of 0.75 times 1 minus p, which is 0.25, over n, which is, we gathered a sample size of 100, and this is equivalent to, 0.75 times 0.25 divided 100. .0433 approximately. So as you can see, are similar to section 8.1, as n increases, sigma decreases, especially compared to, actually we didn't calculate it, but if we calculated the standard deviation of the original distribution, which is actually going back to this page, I'll just show you really quickly. If you solve for sigma, put in 0.75 and 0.25, you'll notice that it would be larger than this value. I'm not going to go ahead and do that. You can do that yourself. It's pretty easy. And so similar to section 8.1. So there's a lot of similarities. Instead of x bars, we're dealing with p hats. And so p hat, again, is defined as the amount of successes x over n. That's how it how we define it in the book. But it's kind of it's very obvious that you just count up the amount of ones, and then you divide it by the sample size. So it's essentially an average. You're taking the average of this. You can picture it this way, and I think it's really nice to see it like this because it really makes a connection with 8.1. We're following the same exact process. Just this is actually an x bar of this value, but this is a special distribution that we call p hat. And anyways, that is kind of about all we have on section 8.2. It's pretty straightforward. The only other thing that I kind of want to do is quickly talk about the large enough sample size. I mentioned it briefly before, but the NP NP 1 minus P is greater than or equal to 10. That will give us a normal distribution if this is true. And in this case, we have n equals 100 for this example. We have p equals 0.75. and we have p, yeah, so 1 minus p, and this is equivalent to 18.75, which is obviously greater than 10. So yes, since we gathered, since n p 1 minus p is greater than or equal to 10, since we have a sample size of 100, then the sampling distribution is normal. Okay, so kind of a similar characteristic. I mean, this is parallel to, comparing like n is greater than or equal to 30. In section 8.1, when we have a non-normal distribution, we need n greater than or equal to 30. When we have a non-normal distribution with the proportion, and the proportion is always non-normal, so we always have to do this comparison. So np times 1 minus p is greater than or equal to 10. We have to do that. So, and it's true in this case. And if you want to think about it, you know how we had n is greater than or equal to 30 back in 8.1? You can kind of think of it as if we divide both sides by p 1 minus p, we would get n is greater than or equal to 10 divided by p 1 minus p. So in this, so as you can see, let's actually just calculate how large of a sample size we need, the minimum actual sample size we need in order for it to have original, in order for the sampling distribution to be normal. So let's go ahead and calculate that. Actually, I really don't care. Let's just go do it. So in our case, we have p equals 0.75. So we have equals 10 over 0.75 times 1 minus 0.75. And so we have 10 divided by 0.75. So we actually needed a 53.3 repeating. So we needed a sample size of 54 in order to obtain a normal distribution. So as you can see, in section 8.2, that n greater than or equal to 30 doesn't work with this Bernoulli distribution. With the Bernoulli distribution, with p equals 0.75, we needed an n of at least 54 to obtain a normal distribution. So that n greater than or equal to 30 does not always work, but we're just assuming it's going to work when we're dealing with the sampling distribution of x bar. So anyways, yeah, so that is about it. Now, I just wanted to make a quick chart to kind of summarize what we've done in 8.1 and 8.2. So let's see here. I guess we can do actually one quick example before we do that. Let's say we wanted to find the probability that at least 80%. Just making up this problem. What is the probability from this last example? Probability that 80 that at least 80% of the sample of size 100 like ice cream. Yeah, brain fart. Okay, what is the probability that at least 80% of the sample of size 100 like ice cream? So what we're asking for here is what is the probability that p hat is at least, so that's greater than 0.8, 80%. Now we know that that the probability, using the equations that we've dealt with in this section, that and we've already solved for some of this information, just to kind of, I'll show you where it comes from in a moment, that z, we can change this into a a standard normal distribution, is greater than, because the inequalities don't change yet, at least, 0.8. So 0.8 minus 0.75 over 0.0433. So just to show you where these values come from, the 0.75 is the is the center of this distribution, and the 0.0433 is the standard deviation, or the standard error of this this distribution. Since we're taking a sampling of size 100, so that means we're taking a sample. We're taking a sample of size 100, and that's just one value from this distribution. Then the shape of the distribution is mu sub p hat is the center, and the spread, the standard deviation, is sigma over the square root of n, 0.0433. So we obtain this to obtain a z-score. So we would do the following: 0.8 minus 0.75 divided by 0.0433, 1.15 approximately. The probability that z is greater than 1.15, and this is just a basic read the z-score table, or use that normal distribution CDF. So we'll just do a quick. This would be normal CDF of, so the lower bound is 1.15, since it's greater than 1.15, and up to 10,000, or just do 1,000, that'll work. And notice that I'm plugging in the z information, the standard normal distribution. So in this case, the mean of a standard normal distribution is 0, and the standard deviation of a standard normal distribution is 1. You should remember that. And we can plug that in and find the probability. So we have, again, we would go to second. I'll just show you. Let's not have a glare. Okay, so we would go to second vars, normal CDF, and we would do 1.15, comma, 1,000, comma, 0, comma, 1. And we can see that this is about 12.5%, 0.125 approximately. Approximately 0.125. So there's a 12.5% chance, or 12.5, or the probability of 0.125 that at least 80% of the sample of size 100 like ice cream. Okay, so that's just an example of finding a probability. It's pretty much identical. It's just the probability that the p hat we're concerned about minus mu sub p hat. So just to show you where this equation, actually we're going to show you on the next page. So keep this in mind when we go on the next page. Yeah. So section 8.1 We have, let's just say, a normal distribution. I'm talking about the original distribution. If the original distribution is normal, if the original distribution is normal, and let's just say, and we're given mu and sigma, okay, and then there's also the possibility of a non-normal where we're given mu and sigma. And then there's also the possibility that we have a non-normal. I mean, this is non-normal, but actually, again, this is called a Bernoulli distribution. And we're just given P, the population proportion. So those are three different possibilities for the original distributions. And then we know that we have a normal distribution for the sampling. So sample distribution is normal if, and I'll just say always normal for the first case, as we mentioned before. In this case, n is greater than or equal to 30. And here, for a Bernoulli distribution, np 1 minus p is greater than or equal to 10. And then we also know that the shape of this distribution in so let's just write it right here. For both of these cases, I'm just going to write it once. For both of these cases, you have mu sub x bar equals mu. Okay? And then you have sigma of x bar is equal to sigma. So keep in mind where we're getting this information. It's from the original distribution, sigma over the square root of n. And then we have, for the Bernoulli distribution, where we're just given the population proportion, mu sub p hat, since we're trying to, our sampling distribution is of p hat, mu of p hat is equal to p. It's directly equal to this. It's going to be centered at that always, if you're taking the average of the averages. Similar to the center is this. Okay, for the normal distributions. Let's just write a line like this. Okay, so, and then sigma of p hat is equal to the square root of p 1 minus p over n. Okay? And so that's just a kind of a summation of section 8.1 and 8.2, all of chapter 8. This is about all you need to know. Just double checking here. Seeing if I have all the equations. Oh, yeah. So the z-score equation, if you can imagine it, it's always, so I'll just say 8.1, 8.2 for these two and that one right there. So in 8.1, the z-score equation, standardizing our distribution, would be x bar. So we're going to, we'll be asked about some sort of x bar, and so we'll be plugging in an x bar, and then we'll be doing, we would be subtracting mu over sigma over the square root of n. So as you can see, you just plug in mu here, and you plug in sigma over the square root of n here. So essentially, this is equal to x bar minus mu sub x bar over sigma of x bar. See that? Just substituting the values in. So this looks very similar to the original z-score equation that you would have seen in chapter 7. And similarly, A.2, like with the Bernoulli distribution, we have z equals p hat. We'll be asked about some sort of p hat, like we were asked something about x bar, minus p over the square root of p1 minus p over n. And that is equivalent to, if you look at the values that we have up here, that is equivalent to p hat minus mu of p hat over sigma of p hat, just substituting the values that we see right here. And as you can see, the similarities between 8.1 and 8.2 are sampling distribution. The sampling distribution that we're talking about in 8.1 is x bar. And the sampling distribution that we're talking about is p hat in 8.2. And as you can see, it's the same exact equations here and here, except for instead of having x bars in right here and in the subscripts here, you have p hats in here and the subscripts here. So they're very similar. There's direct parallels between the two. It's just we're measuring different type of samples, x bars or p hats, trying to estimate sort of like what mu looks like or p looks like. So very similar. So let me know if you have any questions about 8.2. And this is just a really good reference and when you're trying to work on chapter 8 homework, this page right here. And it kind of goes over a lot of this at the end of the chapter on the chapter 8 review page. It goes over a lot of this information. So it's a good reference page. Let me know if you have any questions. Okay, good luck.